Warm welcome to everyone joining us. Come on in, get yourself ready. Grab a notebook, a pencil or pen. Anything you want to write with is fine. This is math from the void. Math coming at you out of nowhere. Today we have a problem from the 1993 AP Calculus AB exam. Go ahead and give yourself a chance to work this out yourself. You can pause the video. See, there's a very simple graph that goes with it. And, give yourself about maybe 10 to 12 minutes. This one's a shorter one. And when you're ready, you can join back and we'll get started. Okay, so the figure above shows the graph of f prime, the derivative of f. So this is, they made it very clear, this is not the graph of f. This is f prime. I'll even write f prime. And the domain is simply from 0 to 2. The domain of f doesn't include 0, and it doesn't include 2. That's kind of useful to pay attention to there. Okay, number one, or part A rather, really easy. Write an expression for f prime in terms of x. So this is pretty clearly just an absolute value function. If you can't see that that's an absolute value function, you definitely need to go back a little further than I would have expected to review that. So this is an absolute value function with the equation negative absolute value. It's shifted to the right by 1, and it's also shifted up by 1. So there's a perfectly valid expression in terms of x. I guess we can put this right here. X minus 1 in the absolute value, and then plus 1 on the outside. Okay, pretty simple. Now, here's the thing. You can tell that the absolute value function is two different lines. It's possible that we're going to need to split it up into two different lines as a function. It's possible. Not entirely certain, but we'll see. So part B wants us to say that given this initial condition, sounds like we're going to have to go backwards to f at some point, write an expression, there you go, for f of x in terms of x. So it's going to be difficult to take an antiderivative of absolute value. If you think about it, you probably haven't really done that very often. So how do we take a derivative even of absolute value, or an antiderivative of absolute value? Well, it's going to be a little bit tough, because we can't simply say, oh yeah, let's just add up the area here. We can't just do that. We are going to need to use the area at some point for the initial condition, it seems like. But let's get a better description for this absolute value function. Now, in case you forgot, and you should check out my video on absolute value if you forgot, the absolute value function is a piecewise function. It's split into two pieces. As you can see, there's like a piece that goes up or a piece that goes down. Whether it's flipped or not, there's a piece that goes up and a piece that goes down. So if we just have the regular absolute value, this is just equal to x as long as x is bigger than or equal to 0. But it flips it to negative x whenever the number you plug in is negative. So if we adjust this a little bit, this function, to fit what we actually have, and let's call it f prime, which it is, this is negative absolute value of x minus 1, and then plus 1, which means this is simply going to leave the x minus 1 and then plus 1, as long as the inside x minus 1 is greater than or equal to 0. There's already a negative out front because of the function. It's a flipped over absolute value. So that's where this negative comes from. And hold on to your hats, because this is going to be negative, and then the inside of the absolute value gets flipped, which means we have negative. That happens whenever the inside actually gets flipped, which means the inside x minus 1 is less than 0. Okay, so now we're about to have a pretty nice description for the derivative. Let's simplify things a little bit. That means this is negative x plus 1 plus 1, and this is whenever x is greater than or equal to 1. And that seems about right. That's this part of the line with the negative slope. It would go through y equals 2 on the y-axis. And then on the other hand, the negatives cancel here. So negative negative is just x minus 1, but then plus 1. So it's just x. That kind of makes sense. That's what this line is. But it doesn't go forever. It only goes until x approaches 1. So whenever x is less than 1. Now, this is much, much easier to take an antiderivative of. Okay? And they give us the initial condition that f of 1 equals 0. So that's going to help us out a little bit with an expression for f of x. Okay? So we know that f of x is simply going to be the antiderivative, or the indefinite integral, of f prime, which means that it's going to be split into two domains. It's going to be the antiderivative of negative x plus 2 whenever x is greater than or equal to 1, and it's going to be the integral of x whenever x is less than 1. Okay? Do we know that this is continuous? Yes, we do, because its derivative, right? Its derivative is defined the whole time. Even at this breaking point, x equals 1, the derivative is defined, which means the function is continuous and it's smooth. Now, the derivative of the derivative is not smooth. The slope of the graph we're looking at is not smooth because there's a sharp corner, which means its derivative has a jump. But we're not talking about the derivative of f prime. We don't need that at all. We're going backwards and talking about f. So here's the interesting thing about this problem, is that when we take the antiderivative, of course, we're going to get the plus c, right? So this is going to be negative x squared over 2 plus 2x plus c. And that is, again, when x is greater than or equal to 1. This one, on the other hand, is going to be x squared over 2 plus, and I'm not going to call it c, or I guess I could just call it c2. These are not going to be the same constant necessarily. It's possible that it will, but just thinking about it right off the top of my head, I don't think that we can assume those are the same. It's possible they have the same shift, that way they're connected, but I'm not going to assume that. So here's what I'm going to here's what I'm going to do. I'm going to say that given this definition of f of x, right, this is all equal to f of x, I'm going to use the fact that f of 1 equals 0, or was it f of 0 equals 1? No, f of 1 equals 0. I'm going to use that fact to say that if I plug in 1, which means I'm plugging it into the top function, negative 1 squared over 2 plus 2 times 1 plus c, that all needs to equal 0, so I can find my c value. So this is going to be negative 1/2 plus 2, which is just 3/2, plus c. So c equals negative 3/2. I know that for sure on this top function. Negative x squared over 2 plus 2x plus 3/2. Oh, sorry, minus 3/2. Now, since I know that these two are connected, I know that this has to be equal to x squared over 2 plus c2, I know that they have to be equal because it has to be connected at x equals 1. How do I know it's connected? Because the derivative exists. And the only way the derivative exists at a point is if the graph is differentiable, which means it's smooth. And if it's differentiable and smooth, it's definitely connected. In fact, it doesn't even have to be differentiable for it to be connected, but the fact that it is differentiable means it definitely is connected. Okay, so let's set these things equal to each other. That means that x squared over 2 plus c2 also needs to equal 0. They need to equal the same point. And if I plug in x equals 1, I guess I should say, oops, I should say 1 squared over 2 plus c2 has to equal 0, because again, this already equals 1. This already equals 0. And so this also has to equal 0 in order to connect. So 1/2 plus c2 equals 0, and there you have it. They're not the same values. c2 equals negative 1/2. So overall, f of x is equal to negative x squared over 2 plus 2x minus 3/2. That's whenever x is greater than or equal to 1. But if x is less than 1, this is simply going to be x squared over 2 minus 1/2. And there's my expression for f of x. Very nice. Okay, last part here. In the plane provided, I didn't really screenshot the plane provided, we can just do that. Sketch the graph of y equals f of x. Okay, so not too bad at all. You just have to sketch this. Let's see, I can probably find the axis of symmetry and on these parabolas. Let's see if it occurs anywhere on the interval. I know for sure, obviously, at 1, we're at 0 for both sides. And let's see, I'll draw this piece first, the piece on the left. I know that when x equals 0, y equals negative 1/2. In fact, I also know that that's the vertex, because the vertex occurs at x equals 0 for this parabola, which has not been shifted left or right. It's just been shifted down and stretched. So the symmetry tells me that I'm also going to get a point at negative 1, 0. It goes up kind of like that. If I wanted to plug in more points, like if I want to plug in, I don't know, negative 2 squared, 4, over 2 is 2, minus 1/2 is 3/2, so that's roughly where this would be. This would be at 3/2. All right, now let's look at the other piece. The other piece is a sort of upside down parabola, and its y-intercept would be negative 3/2. Notice that. So where is the axis of symmetry on this one? We're going to have to use the old negative b over 2a trick. Negative b over 2a, that's going to be negative 2 over 2 times negative 1/2. So that's at positive 2. Okay, the vertex is at positive 2, comma, let's see what the y value is. So we'll say f of 2 equals negative 2 squared over 2 plus 2 times 2 minus 3/2. 2 squared is 4 over 2 is 2. So negative 2 plus 4 minus 3/2. That's 2 minus 3/2. That's only 1/2. So at x equals 2, we have a point at y equals 1/2. That is the vertex location. Oh, it's a little too close. I like that a little bit better. Okay, and I'm going to use a different color just so that it's really clear to you guys that this is the other part of the function. And since it's symmetric, all quadratics are, they're all symmetric over the line of symmetry. We're also going to have a point here, and then it'll just kind of go like that. Okay, so that's a perfectly valid sketch here. We have 2, 1/2. We have 3, 0. We have 1, 0. We have 0, comma, negative half. We have negative 1, comma, 0. Oops. Like, we have plenty of points here now. Negative 2, comma, 3 halves. That's plenty of values there. Okay, so that'll do it for our sketch. All right, now this one was particularly interesting because they gave you an absolute value function for the derivative, and then you had to integrate, which means you have to use the definition, the piecewise definition of the absolute value. And when you get two separate integrals, because of that, you have a separate plus c for each. So you have to be on your toes with a problem like this. Then lastly, graphing it is just like some basic algebra 2 skills, nothing important there. But it's important to get like more than 4 points, especially some intercepts if you have them. So we have 4 intercepts. We have 3 x-intercepts and 1 y-intercept. That's already pretty good. And then this vertex is kind of important. And I don't even think this negative 2, comma 3 halves is that important. But all of these things support your answer, so they contribute to you getting points. All right, that's enough blab out of me. See you guys next time on The Void.